Hi everyone, in this video we are going to be solving a 3x3 system of linear equations using Gaussian elimination and then back substitution. So we use Gaussian elimination to get our system into what's known as row echelon form. So sometimes we call that the stair-step solution pattern with the leading coefficients of each of the variables to be 1. So we want to end up with a system of 3 equations where the coefficient for x in the first equation is 1, the coefficient for y in the second equation is 1, and the coefficient for z in the third equation is 1. Essentially, in the third equation, we'll have z equals a particular value, and then we'll be able to use that value of z to back substitute and solve for all 3 of the variables. There are 3 possible solutions that can happen when you get a system of linear equations. In this case, our systems are 3 dimensions. So if the systems intersect at one point, we can visualize that as 3 different planes intersecting at one point, and we call that exactly one solution, a consistent system. The other possibility is all 3 of these equations could actually be the same plane. So then they would intersect everywhere, and we would say that's also a consistent solution or a consistent system with infinitely many solutions. The third possibility is that the planes don't intersect, and so we would say that the system has no solution or call that an inconsistent system. So let's explore and see how we can solve this equation using Gaussian elimination. The first step I want to do is eliminate the x variable in the second equation. So I'm going to do that by creating a new second equation. I'm going to say equation 1 minus equation 2. So I'll go ahead and annotate that. I'll use red for that calculation. So equation 1 here is x plus y plus 2z equals 2. I'm going to cross my z's because they might look like a 2 otherwise with my handwriting. And then I'm going to subtract my second equation. So I'm going to say minus x. I'm going to go ahead and distribute my negative through. So this will be a plus 2y. And this will be a minus 8z. And this will equal 2. And then what this does is we've eliminated the x variable. So we get 3y minus 6z equals, oh, this is a negative 2, so this should all equal 0 here. Now you might have subtracted in the other order. You would have essentially the same equation, just a difference of signs. In this case, either way, we're going to get 3y equals 6z because this equation is equal to 0 here. All right, let's go ahead now and rewrite our system in terms of our new equations and see what we can do for equation 3. So our new system now, I'll write it in blue, is x plus y plus 2z equals 0. No, I'm sorry, equals 2. I'm leaving my first equation unchanged because it's in that form already with coefficient 1 for the x, so I'm happy to have that result. And then I'm going to manipulate my second equation. I already did that, so I'm going to rewrite that as 3y minus 6z equals 0. And now my third equation is negative x plus y equals 4. And so I want to rearrange the third equation to get that in terms of z. So I'm going to say equation 1 plus equation 3 because that's going to cancel out my x values here. So I'll write that over here in green. So I'm going to say x plus y plus 2z equals 2 for equation 1. And then I'm going to add up with equation 3. And so my x's cancel out, and I end up with 2y plus 2z equals 6. We want to have a z variable by itself in the third equation, so that's why we've gone through this step. And so now let's go ahead and rewrite our system of equations in the next screen. So our first equation remains unchanged. It is x plus y plus 2z equals 2. Our second equation is now 3y minus 6z equals 0, this equation right here. And our third equation is this new equation that we've worked out, 2y plus 2z equals 6. So I want to get z by itself in the third equation. So I am going to do that by taking equation 3 and equation 2 and rearranging them. First, though, I'd really like to have the leading coefficient in equation 2 be a 1. So I can do that by multiplying through by a constant. So I can multiply all of equation 2 by 1/3. It's going to be consistent as long as I do it on both sides. And then I will have a nicer looking system over here. I will have x plus y plus 2z equals 2 still for my first equation. But now my second equation is y minus 2z equals 0. And that makes me a lot happier because now I've got leading coefficients 1 for both x and y. And I'm getting closer to that row echelon form that we're hoping to get. So now our third equation is 2y plus 2z equals 6. And now what we would like to do for the third equation is to get z by itself there. So I am going to be able to do that by saying, let's see, equation 3, subtract 2 of equation 2. So we'll say 2y, this is equation 3, plus 2z equals 6. And then we're going to subtract double of equation 2. So that'll give us a minus 2y to subtract out our y's. And then this is going to become a minus 4z equals 0. And when we add all this up, we get negative 2z equals, I think I missed something here. This is going to be a plus here. See how easy it is to make mistakes when you're working this one out by hand. And then this becomes a 6z. We get 6z equals 6. All right, so now we can divide both sides through by 6 and get z equals 1. So you can see it's easy to make calculation errors here. And so actually we are going to be working with computers more often because that's a more efficient way to solve these equations. So now let's rewrite our system. So we've got now our lead equation is still x plus y plus 2z equals 2. Our second equation is y minus 2z equals 0. And now we've got z equals 1 for our third equation. So we are going to back substitute into our second equation to solve for y. So y minus 2 times 1 equals 0 tells us y minus 2 equals 0, or y equals 2. We can go ahead and box in our solution so far. And then our last work is to solve for x. So we can say x plus 2, plugging the y value, plus 2 times 1 equals 2 here, plugging in our y and z values. So x plus 4 equals 2. Well, that tells us then x is negative 2. So we have solved for the point where these three systems intersect. You can visualize it as 3 planes meeting at one point. So we say this is a consistent system with one solution. All right, let's go ahead and look at the next example of this system of equations. So notice in this system of equations, our first two equations remain the same, but our third equation here is a different equation, a different plane if we're visualizing it in 3D. So we want to see where do these intersect. So we can do the same move we made earlier and do equation 2 minus equation 1, or equation 1 minus equation 2, our preference. So let's do a little different. Let's do equation 2 minus equation 1. So we'll say x minus 2y plus 8z equals 2, and then subtract out equation 1. So we'll have a minus x minus y minus 2z equals negative 2. My cat is here, if you notice him in the background of the video. He likes to join me sometimes when I'm doing videos. So we end up with a negative 3y plus 6z equals 0. So you can see this is just the opposite signs, but the same equation that we got in the earlier problem. It's your choice which equation you subtract. And now we want to try to simplify equation 3. So let's do equation 3 and subtract 2 of equation 1 to try to get rid of the x's there. So we'll say equation 3, which is 2x plus 5y minus 2z equals -3. And then we want to subtract double of equation 1. So it's going to be minus 2x minus 2y minus 4z there equals -4. So we end up with our x's canceling out. We get 3y minus 6z equals -7. So this looks similar to the equation that we had here in equation 2. It's different by a sign, and then they're equal to different values. So if you're feeling suspicious, you should be, because it doesn't seem like it's going to work if one version of this equation equals 0 and another version equals -7, and their only difference is by a sign. So let's look what happens if we take our system and try to simplify it further. So we'll leave equation 1 unchanged. Equation 2 is now -3y plus 6z equals 0. And equation 3 is 3y minus 6z equals -7. So let's see what happens if we try to simplify equation 3 by saying equation 2 minus equation 3. What's going to happen there? Well, on the left side, everything cancels out. So we get 0 equals -7. Well, that's false. So as soon as we run into a false solution, that tells us this is an inconsistent system. These planes have no intersection. So we've got some parallel planes going on here. And so we see that when we simplified equations 2 and 3, that they were essentially the same equation with different values equal to. So if you remember back from algebra, that when the slope is the same, but you've got different starting values or different intercepts, then you've got parallel lines. In this case, in 3D, this means we've got parallel planes here. So this is an inconsistent system. We'd say there's no solution. So in conclusion, there are 3 different types of solutions you'll see to systems of equations. You'll see inconsistent systems where there's no solutions. If we had gotten something like 0 equals 0 or 7 equals 7, that would mean that there were infinitely many solutions and we're working with the same equations. And so that would be where all the equations are the same plane. And then the last possibility is a consistent system with one solution.